Good afternoon. So welcome back. For those of you who were at our lunch today, it was quite engaging. It was a great lunch, and we had a great speaker with Greg Olson, talking about his time in space, how he got there, as well as the wine that he gave to the event, which we enjoyed very much. So I hope I didn't have too much of it before starting the talk today. But, Artemis was worried that I might not have something to say today, so she sent me this script, in case I was tongue-tied. So I figured, just imagine me as Artemis right now. I'm just going to read Artemis's speech to introduce the moderator of our panel, actually, Les. So, imagine Artemis. In space propulsion is all about getting where you want to go as cheap and safe and as fast as you can. That doing so is smart. That doing so is smart goes without saying. That doing so might learn us things about how to do things more sustainable on Earth and less obvious. That doesn't make sense. On Earth is less obvious. Les Johnson knows that space can give us particularly limitless energy and raw materials, which means that thinking up new ways, better ways of propulsion in space is not a geek dream. We're not calling any of you geeks, but a very down-to-earth, no pun intended, approach to getting the best out of all of us in a sustainable way. Les, please introduce your panel now. Sorry, I kind of screwed up part of that introduction, but I can't be Artemis. So.
All right, thank you.
I'll take my name tag off and put yours on.
Okay, very good, thank you. Well, good afternoon. Hope you all had good lunch. I wasn't able to go to the banquet. We instead were in a deep huddle preparing for this afternoon's panel. At least some of us were able to be there and do that. I'd like to welcome you to the In-Space Propulsion panel. And today I'll introduce the topic and our speakers, and then each of the speakers are going to have just a few minutes to talk about some pre-prepared thoughts about the in-space transportation and propulsion challenge, which are not always the same thing. And then we'll have some questions and answers and hopefully get you guys engaged in that. I'd like to introduce all of the panelists first, and then we'll go through and have them talk a little bit later on. The first panelist I'd like to introduce is Mike Houts. I've known Mike for several years. He currently serves as the Nuclear Research Manager for NASA's Marshall Space Flight Center nuclear research work. He's been there for 13 years. He's responsible for guiding research related to the design, development, and utilization of space nuclear power and propulsion systems. His qualifications for that come from the many years he spent at Los Alamos National Laboratory, where he was the team leader for criticality, reactor, and radiation physics, and the deputy group lead of the Nuclear Design and Risk Analysis Group. He has a PhD in nuclear engineering from MIT. Next over is Roger Myers. Dr. Myers is the Executive Director of Advanced In-Space Programs at Aerojet Rocketdyne. He oversees programs and strategic planning for the next generation in-space missions and architectures, propulsion, power, and integrated systems. Prior to this appointment, about 2 years ago, he was the Executive Director of Electric Propulsion and Integrated Systems and the Deputy Lead for Space Launch Systems and the General Manager of Aerojet Rocketdyne's Redmond operations. He has a Bachelor of Science degree in Aerospace Engineering from the University of Michigan and his PhD from Princeton. Next over is Mark Carter. Mark is presently the Senior Vice President of Technology Development for Ad Astra Rocket Company, where he's worked since 2006. The company's focus is on the commercial space applications and development of the VASIMR, the radio frequency-driven plasma rocket that you've probably heard about. He received his PhD in nuclear engineering with a minor in physics from the University of Wisconsin at Madison. Prior to coming to Ad Astra Rockets, he was for over 23 years on the staff at the Oak Ridge National Laboratory. And finally, I'd like to introduce also Andrew Petro. Andrew is the Program Executive for Solar Electric Propulsion and Small Spacecraft Technology in the Space Technology Mission Directorate for NASA. Prior to coming to headquarters, he worked at the Johnson Space Center in Space Shuttle mission operations and in their engineering directorate for advanced space propulsion and lunar transportation. In fact, he was a project manager for the NASA Advanced Space Propulsion Laboratory, where he worked on plasma rocket designs. So you can see we've got a panel that are comprised of in-space transportation experts in various disciplines. Many of these are advanced in-space propulsion systems that we haven't yet fielded for human and robotic exploration in deep space, and I hope we can get some new insights for us today on those challenges. To start out with, there is one big challenge, and the two big challenges for going anywhere in space. And I like to joke with my colleagues at Marshall, being from the Marshall Space Flight Center, is that I think the rocket guys to get us off the ground have the easy part. That's the first 300 miles. We typically have the next several hundred million. And don't underestimate that. I mean, the challenge of going places in the solar system is one of distance and time. And personally, I think we tend to underestimate and often underutilize that. And I'm so encouraged to hear that we're moving toward the thought of solar electric propulsion for cargo, because in that way, you take advantage of the fact that you know you're going to have a lot of time to get where you're going, so you might as well do it as efficiently as possible and cut down on the launch mass and get the simplicity of the system architecture where you want it to be. It's that kind of thinking that should dominate how we think about deep space exploration, and instead of fighting nature and fighting the situation, figure out how to work with it and use it to our advantage. And if you look at the chart here, I think we all know this, when we're talking about deep space propulsion, we are currently not targeting the moon as our primary destination. We've got asteroids as a target, and we've got Mars as a target. Our international partners are talking about going to the moon, and all of these have in common the need to go from low Earth orbit to those destinations with some kind of an advanced in-space propulsion system. It's my personal opinion, over the next several years within NASA, we probably won't develop 3 or 4 human-rated deep space propulsion systems. So as we move forward on this challenge, I believe we need to have forethought into what the various targets are going to be. And yes, we may sub-optimize for any given one, but given the budget realities we have, we need to have in mind the destinations that we think we're going to go to and think about how to evolve and scale the systems to support all of them. Because we're talking about trip times from as short as 3 to 7 days all the way out to the better part of a year. Not saying anything new to most of this crowd. One thing we do tend to underestimate is this distance problem. I see a lot of charts in the public mind that discuss the distance in terms of how many AUs from the sun the various targets are. Well, that discounts the problem that we're not in the Enterprise, and we can't just zip from here to Mars when it's at its closest approach at about a half an AU, right? We have to have a trajectory that's going to put us on some kind of an arch that's going to take us through the solar system that can be 400 million miles or more, far more than just the separation distance of the planets. So we've got this incredible distance we have to cover, and that translates it to time, and what we really need to do is minimize this for the crew, whereas I contend it doesn't matter as much for the cargo. But keep this in mind as our panelists are speaking today. I've been involved in various architecture studies for human exploration, looking at Mars, looking at asteroids, looking at the moon. And this is kind of a high-level shopping cart, as it were, for the various types of propulsion needs you have to go to these various destinations. And these are kind of the traditional space of those propulsion options and how they fall out. And this gets us into a dangerous way of thinking. And that way of thinking is very specific destination-oriented, when, again, in my opinion, we need to be thinking of those myriad of possible destinations and how do we optimize the choice of propulsion system to allow us to have that flexibility as we go forward into the solar system. Everything from moderate delta V for near-term destinations to very high delta V, which are required for Mars, near-Earth asteroids, and other deep space destinations. So we need to be thinking about that and looking at these options and asking ourselves, are these really the right options, and how do we neck this down so that we still have flexibility but don't overextend ourselves in investing in too many things that we ultimately won't be able to afford. That said, please don't quibble with any of the individual numbers here. This is a distillation of years of architecture studies and various configurations and ground rules and assumptions in terms of what kind of launch mass you have to get to various destinations with crews of humans. In fact, these are not even consistent ground rules and assumptions between the different categories of technologies we have here. What's important is to look at the relative order of magnitude of these launch numbers, launch mass requirements, in terms of the type of propulsion system that has been studied for these various systems. If you go with an all-traditional chemical propulsion approach, you've got a lot of mass to get off the planet. If you go to something that has a higher ISP, you can significantly reduce that launch mass, mainly in terms of not using all of that launch mass for propellant. And you get into other trade-offs. For instance, the development of nuclear power versus high-power solar electric. Do you have nuclear thermal, nuclear electric? Do you go with the combination of solar electric for cargo, combined with either chem or maybe with nuclear thermal for the sprint of the humans? And these numbers will vary, but you can see here that efficiency in rocket propulsion performance, whatever kind of rocket we end up having, is very, very important to where we go. And before I hand it over to our first speaker, one of the topics we were talking about before we came up is our experience in architecture studies, speaking, again, personally at NASA. And maybe it's because of the knothole that I fit in as a former manager for in-space propulsion technologies for NASA. And that is that when you look at the architecture systems, we always seem to immediately start designing the crew transfer vehicle, the launch vehicle, the habitat, the lander systems, the crew systems, and it's almost as if it's an afterthought that, oh yeah, we have to move these around in the solar system. What budget wedge is left that we can apply to develop this advanced in-space propulsion system? And maybe that kind of makes me feel like the Rodney Dangerfield of the space community in terms of propulsion. We don't get no respect. But in terms of the challenges and what often ends up being a limiter and a risk factor for our crews and the lifetime of our systems is that in-space propulsion leg of the journey. So with that, I'll turn it over to Andy and let him give you his perspective. Yeah.
Okay, thank you, Les. As Les mentioned, I actually have two roles in the Space Technology Mission Directorate. One is Program Executive for small spacecraft technology, as well as for solar electric propulsion. Two very different things, although there's an overlap, and that overlap really comes down to propulsion. And so I wanted to take a few minutes to talk about that. We will be demonstrating some CubeSat scale missions toward the end of this year that have simple cold gas propulsion systems demonstrating rendezvous and docking on the CubeSat scale, as well as what we hope will be an actual orbit change maneuver with a CubeSat scale vehicle. But we're interested in expanding that capability with both chemical and electric propulsion on the CubeSat scale and somewhat larger scale vehicles. And we've looked at the kinds of missions you might do with that. And we're very interested. We're making some investments in electric propulsion systems on that CubeSat and slightly larger scale. We have a development project for a demonstration mission of a small Hall thruster using iodine as propellant. Iodine is very interesting because it's a very compact way to store the propellant compared to things like xenon. So we have that activity going on, and so my interest goes from a few watts to megawatts when it comes to electric propulsion. So I'm now going to focus on work that we have underway in space tech, looking at solar electric propulsion and a demonstration of that capability. How do we?
Should just, the right side, should just click it up. Yeah, just push that.
There we go?
Yeah.
Okay, there we go. Okay, so this is where we're making investments right now. In terms of thrusters, we're working on what will be a 10 to 15 kilowatt Hall thruster that would be part of an advanced higher power electric propulsion system, as well as the power processing units that would go with that. Of course, that's a very important part of the entire string. And then propellant feed and storage tanks for what would be up to a 50 kilowatt type system. We're also doing work in the solar arrays. There were two development projects that completed in the past year, one with DSS and the other with ATK, looking at very large, lightweight solar power arrays. They did ground demonstration, including vacuum chamber deployment of these systems. We feel a lot of advancement has been made there toward being able to fly systems of that size that would support these higher power solar electric missions. And you see illustrations of the two solar arrays on the right in their part of their ground demonstration work. At this point, what we're looking at as an initial demonstration of a solar electric system of that size is the asteroid redirect mission. That would employ 3 plus a spare of a 12.5 kilowatt Hall thruster in a package, along with 8 to 10 tons of xenon, a lot of xenon compared to any kind of mission that's been flown before, and packaged in a space vehicle that would have 2 25 kilowatt solar arrays deployed and be able to fly from an injection from Earth out to an asteroid, rendezvous with that asteroid, maneuver to the surface, and you see illustrated the mission concept where the entire vehicle flies down toward the surface of the asteroid, reaches out and grabs a large boulder and would remove that from the asteroid and then maneuver back to a distant retrograde orbit of the moon, where it would wait for an Orion spacecraft coming from Earth with 2 astronauts who would rendezvous with that vehicle, dock to it, and then be able to get out and investigate the asteroidal material that had been delivered to that point. So it's a demonstration of moving a large mass across the solar system with this type of vehicle. And just looking beyond that, of course, it's hopefully the beginning of a whole series of missions that we might then be capable of doing with perhaps with that scale vehicle, the 50 kilowatt type vehicle that would have been demonstrated, but also moving on to larger versions of that, 150 kilowatt or beyond, and larger amounts of propellant as well. And then also looking at a variation of that you may have heard about, combining a chemical propulsion system with that solar electric system to provide an even more capable vehicle for certain types of missions. And so we're very interested in that capability as well. And just looking at all of the kinds of missions we could do, and that's, I think, one of the advantages of things like solar electric propulsion. It's not just for NASA's exploration missions, but certainly has application for a wide range of science missions. Some, I think, beyond what has been considered possible before, as well as things closer to Earth, satellite servicing, or using it as a tug to move things from lower orbits to higher orbits or beyond to the moon. And even in lower Earth orbit for orbit maintenance and things, missions like that. And we're very focused on how other users, other government agencies, and in particular commercial companies could make use of this technology, because we understand if we're the only user, it's always going to be somewhat more expensive for us. We can make things more affordable if we're using the same types of systems that others can use, in particular commercial users. And that may drive some compromises in how we look at things. So to conclude things, I want to make the contention that the solar electric propulsion work that we're doing is a step on a pathway to an affordable, practical solar system access. Again, not simply on the 50 kilowatt scale, but looking beyond that, how we can grow it beyond that, both in terms of the thruster power and efficiency and thrust, as well as the power levels. And of course, to go to higher power levels, and especially as we move further from the center of the solar system out, we're going to begin to require new sources of power, and an obvious choice would be a nuclear power source that you'll be hearing a little bit more about. So we are, at this point, developing the 50 kilowatt scale system. We see ways to fully utilize that capability, scaling it up even a little bit to do a much broader range of missions. And we also see the need to advance that technology to more capable propulsion, thruster systems, as well as higher power and new sources of power. And really allows us to move to real space ships that are able to reach all parts of our solar system in reasonable lengths of time and are reusable. They're not just throwaway vehicles that we've used for decades, but something that makes affordable space travel actually practical. And part of that, along the way, we have to address cost. And things like some of the component technology still remain very high. I've been surprised to see that the non-recurring cost of developing solar panels is high, but the recurring cost, once you've done it to buy more of them, is surprisingly high because the components themselves are still pretty expensive, still a fairly labor-intensive process to build these things up. So we need to, I think, look at the component technologies and get to things that are less expensive, even if we do sacrifice some of the performance. And be willing to make design compromises in order to develop systems that have multiple customers. And I think that's going to be an important thing as we look at how these are used in cislunar space, even in Earth orbit, for science missions, for commercial activities, and every other possible way we can expand that pool of users to make the system for us more affordable. So that's it.
Thank you.
Concludes mine.
Mike?
There we go. All right, well, I'm going to spend just a few minutes talking about space nuclear power and propulsion. But when I talk about that, it's really going to be in terms of fission and not the radioisotope systems. We've had tremendous success with radioisotope systems over the past 4 decades. But when we go to higher power levels, when we go to things like nuclear thermal propulsion, we really need to move on to fission. Now, the key advantages, at least to me, that we're really after is when we go to fission, we essentially remove all of the energy density constraints of the system. Fission itself has about 10 million times the energy density of the absolute best chemical reactions. And so even though there's a lot of other constraints on the system, a lot of engineering that will need to be done, by removing that constraint, that opens up a lot of opportunities for us. And also because the energy comes from fission and not chemical reactions, we have in a thermal propulsion system, we have almost an unlimited choice of propellants. Now, it turns out we choose to use hydrogen because of the low molecular weight. Gives us the highest specific impulse for a given core temperature. But again, we don't need any particular set of propellants to get us the energy. That energy is coming from fission. And so with those systems, the initial systems, they'll have about twice the specific impulse of the best chemical systems, looking about 900 seconds of ISP. But then the advanced systems, the systems that could be built up from that, really have just tremendous performance potential. And so in thinking of an analogy, when we developed the DC-3, it had to have a lot of capabilities. No one would have developed the DC-3 if it didn't do things that couldn't be done another way, if it wasn't affordable, if it really didn't give us some kind of a capability. But it took us 29 years, which is a relatively short period of time, to go from the DC-3 to the SR-71. And so when we talk about nuclear thermal propulsion, really what we're trying to come up with is the DC-3. In other words, we want the simplest, most affordable, easiest to develop NTP or nuclear propulsion system that we can come up with, just so we can actually do it. If we can't afford it, we're not going to do it. And so there's always this trade. If you make it too simple, it doesn't do enough for anybody to get interested. If you make it too fancy, it's too expensive to do it. And so I love that sumo wrestler picture. If you guys saw that this morning, I need to get a copy of that, because that's really what we've got similar constraints, and they're very big constraints. But once we start utilizing this technology, the growth potential is tremendous. I mean, the types of systems that we could get to. And so that's really a lot of what we're what we're trying to accomplish. Fission itself, won't go into too much detail here. We talked to the chemical rocket guys. They think we should be next to free. There was an old quote back in the 50s about how nuclear electricity would be too cheap to meter. Unfortunately, that didn't play out. And the reason, though, that they think we should be almost free is to them, we look like a heat exchanger. And that's really how the system operates. With a nuclear thermal rocket, you have, basically it's a reactor core, and each hex is a fuel element. And you arrange the configuration so it can sustain a chain reaction. And so you're generating a tremendous amount of energy in this core. And it's just controlled on a neutron bounce. It's really simple. There's little control drums. If you rotate a neutron absorber towards this region, it'll tend to shut the power, reduce the power, reduce the reactivity. If you rotate that absorber away from this region, it'll increase the reactivity, the power will go up. So it's a heat exchanger with a simple control system. But compared to a chemical rocket, piece of cake, of course, turns out reality, it's not like that. And really the reason is because our heat exchanger is a nuclear reactor. So there are a lot of constraints and a lot that goes into this design. But again, just looking at we talk about the power density. If I wanted to do, say, a surface power system producing 200 kilowatts thermal, I'd burn a kilogram of uranium every 13 years. And so running out of uranium isn't really a concern in those systems. And even a nuclear rocket, maybe burn a little over 100 grams worth of uranium to do a typical human Mars mission. You're looking at every 1,000 megawatts hour, about 45 grams. So you come up maybe 120, 130 grams of uranium. So again, just to emphasize, one of the big advantages of these types of systems is just the incredible energy density. There is a small ongoing project to look at these systems. We've really been focused in two areas, and this is HEOMD, Advanced Exploration Systems project. A lot of focus is on recapturing the fuels. And we went back and looked at a lot of the fuels work that was done in the 60s. There were a lot of kind of graphite-based fuels that were developed under the Rover Nerva program. There were separate programs looking at CERMET fuels, which are a tungsten UO2. It's kind of a mixture. It's basically 60% UO2, 40% tungsten. Both of them give you very high temperature capability. And you go back and you look at what they did, and you look at their reports. And 3 or 4 years ago, we said, wow, okay, this will be great. So nice, near-term goals. We'll just go recapture that technology. And it was a very humbling experience because what we figured out is, those guys were really, really smart. Because to make that work as well as they made it work, it took just a tremendous amount of effort. We we're making good progress in both areas, but we're also having significant challenges just recapturing the work that was already done. And so that was one emphasis, and this is kind of a near-term milestone that we have. We want to go ahead and try to make a coated graphite composite fuel element, and then actually test it in one of our test facilities. And then another goal that we have, and this is really just starting to ramp up, is to look at some kind of a technology demonstration that could be performed with a nuclear thermal rocket that could also be accomplished fairly quickly. It's not a new idea. Everybody's heard this first bullet from President Kennedy. First, I believe this nation should commit itself to achieving the goal before the decade is out of landing a man on the moon and returning him safely to Earth. Okay, so that's pretty, a very well-known quote. Not many people know the second one, though. Right after that, he says, secondly, an additional $23 million together with $7 million available will accelerate development of the rover nuclear rocket. And so, talking about $30 million to develop the rover nuclear rocket. And so, but when we go back to headquarters and we say, the president said we need $30 million to develop a nuclear rocket, haven't been getting a good response. And so where that led to, though, was the Rover Nerva program. About 1955 to 1973, the duration of that program. Had 20 full power ground tests. This is a engine running out in Nevada. This particular reactor, it was the highest power reactor ever built. Is rated to go up to 5,000 megawatts. One thing that is nice about fission is before fission systems have been run at power, they're essentially non-radioactive. And so you see the two guys, just riding right next to the nuclear rocket, which again we hope would help with launch approval and other handling aspects. But very extensive, very successful program. conducted during that time frame. It's also interesting that the nuclear rocket was the last of the Apollo elements to be canceled, because right when the Apollo program was ramping down, we still thought we were going to go to Mars fairly quickly. And so they kept the funding for the nuclear rocket longer than the other major elements of that program. Just some more specifics of the current program. This is the nuclear thermal rocket element environmental simulator. We can test basically a full-length nuclear rocket element. We can go up to rated temperature. We can test it in flowing hydrogen, but it's a non-nuclear test. And so we can't quite reach the power densities that we would see in a nuclear rocket. And there's also, because we're using non-nuclear heating, it's very good for certain types of tests, but it's not as good for other types of tests. And so, again, but that's on a fairly limited budget in a short period of time. It's going to be actually a very useful test capability. And so there's been a lot of talk about how to make nuclear propulsion affordable. And I think when people look at the architectures and how do we get done in a relatively fast period of time, how do we stay within a budget? A lot of times we saw like the JPL architecture, great architecture, by the way, but of course they ruled out NTP very early in their discussions because it has the potential to be very expensive. And so one of the things that we're really working hard is how can we be innovative and get the cost of NTP down? Now, there's certain words that you can say in some contexts and you can't say in others. As soon as you say innovative in nuclear, everybody immediately thinks, well, you're going to try to be unsafe, you're going to do this wrong. No, we're not talking about that at all. We can be innovative, actually make the systems, in some respects, potentially safer, but also get the cost down. And so just have some ideas for how we're going to do that. One is consider using low-enriched uranium instead of highly enriched uranium. I think John Grunsfeld yesterday, he mentioned he's talking about international cooperation, and he mentioned the policy changes needed, and this was right in the context of NTP. Policy changes for a lot of international cooperation in these areas could be harder than the Mars mission itself. And I thought hopefully he was just being a little colorful there, and that's good. But you can kind of see his point. I mean, this becomes a very sensitive area. Well, when you go to low-enriched uranium, that essentially removes I wouldn't say all, but many of those constraints. And the main backup for that is, whenever we're having discussions with nations about enriching uranium, it's always to just keep it at low-enriched uranium. Don't go into high-enriched uranium. We've basically told every nation in the world that we're happy with them using low-enriched uranium. We've developed fuel forms that are ideal for using low-enriched uranium that we essentially give away to other countries. And so that helps in this area a lot. And also, though, you have turns out in the thrust range of interest for NTP has a minimal performance impact. One of the things, if we are going to go to LEU, you have to be very careful. There's some systems where you really want to stay with highly enriched uranium, even with the cost and the schedule impacts. But other systems, it's really not, doesn't hurt that much on performance. And so for certain NTP systems, especially in the thrust range that we're interested in for human Mars missions, doesn't appear to have a significant impact. There'd be no political opposition based on safeguards. Again, can't overstate the difference between LEU and HEU from a safeguard standpoint. And then, of course, you reduce the security-related impacts on cost and schedule and significantly increasing the programmatic flexibility. There's a lot of talk about trying to get meaningful involvement from industry, meaningful involvement from universities, meaningful involvement from NASA, get all the right players, in addition to a lot of work that would be done by the Department of Energy. But to really enable this optimal team, really need to be able to move to a type of system where all of those players could work on it. Again, give us the programmatic flexibility, let us do the designs where we'd like to, the testing where we'd like to really try to keep the cost down. So keep emphasizing the affordability. State-of-the-art modeling and analysis techniques. A lot of work can be done with multi-physics modeling. There's a lot of data that's been generated over the past several decades that we could draw on to benchmark those codes. That's going to be important for affordability. Dual use when possible. There are fuels, for example, that we could use that could not only be used for nuclear thermal propulsion, but also be excellent fuels for, say, a surface power system. Some of the, I think the ISRU number was a kilowatt for every 305 kilograms of oxygen produced per year. So say we needed 100 kilowatts on a surface, 200 kilowatts on a surface. Well, we could develop fuels that would be cross-applicable, maybe dual use, where you could use this, the fuel, different operating conditions, but a fuel that could be used in your nuclear thermal rocket could also be used for either high power surface power or say a high performance nuclear electric propulsion system, which I think will be talked about next. And again, just a safe, affordable, acceptable ground testing. I think one more chart. The options for ground testing, another benefit that we can talk more details on. Looks like we could go to a fully contained exhaust facility if we wanted to for ground testing by fully containing the exhaust. That should, again, help with not only the potentially on the cost and schedule, but also on the public acceptance. So in summary, fission, it's got a lot of potential. I mean, I don't know how else to phrase it. We've got effectively unlimited energy from it. You can use it for surface power systems. It works any place, anywhere. You can permanently shaded regions. You can be far from the sun. You can be in dusty environments. Nuclear thermal propulsion, choice of propellants, near-term systems, 900 seconds. There's concepts out there where you get into the multiple thousands of seconds. And then, of course, nuclear electric propulsion. And so it's I guess it's one of what Les would describe as one of those technologies that hasn't been developed, shows a lot of potential, and the key is just figuring out how to make it a reality, which means it needs to be affordable and viable on its development path. Thanks.
Good job. So can you bring up just my cover slide? So I'm going to go back a little bit. We've heard a lot about the transportation options over the last couple days, and we just heard Andy and Mike talk about two different pieces of it. But taking a step back, now my first chart. Next chart. Yep. Oh, I do it? I'm in control. Wow, cool. Okay, so this is actually oh, that's interesting. The green did not appear. Oh, it does on that chart. Okay, well, anyway. So this is actually some, we started this journey, so to speak, back in 2009 when we set up this framework for our heavy lift propulsion trade study that we did for Marshall, looking at how do we extend SLS or heavy lift launch vehicles to Mars missions. And we set up this framework, this architecture framework, to look at the different mission phases. And this was our study, again, it was 2009. And the framework is it's a context that helps explain why it is that we are looking at solar electric and things like nuclear thermal or chemical for the crew. We actually traded, again, for the SLS. We have now updated this, obviously, to include the SLS Block 2 capabilities. But for the in-space, to get to our destination, so you see Earth launch there on the left. Not sure how do we use the laser pointer? Is there? Ah, okay. Yes, it does. So here we have the Earth launch, and this is now collapsed to SLS Block 2. Then we have all of the various in-space phases, the descent phases, and you can see there are various different destinations that we were considering in our study. And we looked at lots of options. So we looked at options for the crew and for cargo and logistics, and we looked at both chemical. You can see sometimes they would use the same system in this trade studies. And NTR is there, and SEP, you'll notice, only appears on the cargo and logistics because it's a low thrust option, so it's not going to get crew there fast. And we also considered ISRU. And you saw some of the fallout of this study that we did some years ago in the presentations yesterday with the savings, the mass savings of the ISRU. Bottom line is, all of this told us that the most affordable architecture measured in terms of number of launches and the overall affordability, and again, there should be a bunch of text here that somehow is not appearing, is one where again, you've heard it for the last couple of days, you split the cargo and the crew, and you use SEP for cargo and logistics in the 100 to 300 kilowatt range. And then crew is high thrust, and that's driven by the crew safety requirements. The options, however, are chemical or nuclear, and I'm still in control. So again, you heard Andy, I'm not going to repeat what Andy said, but now there are a bunch of programs in place today that are being executed that will enable Mars cargo and logistics transportation vehicles. There's still ongoing discussion about exactly what shape those vehicles will take, what exact power level, et cetera, but we're talking about modules in the 50 kilowatt range and putting 2 or 3 of those modules together to make your Mars cargo vehicle. So again, those programs are pretty well, we have to continue to execute them, we have to finish them up, but for initial Mars cargo transportation, we pretty much have a solution. So again, the modular SEP approach offers a very low-cost program with a potential for multiple applications. And in fact, you've heard this a little bit. You heard it this morning with the commonality discussion. You heard it just a minute ago from Mike about possible multiple applications for the NTP. But with the SEP, the advantage is that right now that's used a lot commercially. There are lots of missions that use solar electric propulsion. And so this is structuring a program to try to leverage that capability that already exists to enable Mars cargo transportation. The key that we need to still do that we haven't done is we've got to complete the SEP module development and demonstration. That has not been done. This is a major step up in power level. Spacecraft today are flying at 25 kilowatts or so. This is 50. And then it's probably putting 2 or 3 of those modules together into an overall vehicle at the 100 to 150 kilowatt level. So while we have the programs in place, there is quite a bit of work still to be done. Now moving on to Crew, I think Les said it really well when he said, Mars is hard. It's a long ways away. You've heard it a lot recently, but 200 times farther from the Earth than the Moon. A lot more time in zero G, a lot more exposure to radiation, a lot more potential psychological issues associated with being alone out there for many, many months at a time. And so there are real questions about what the crew transportation requirements are. Again, cargo is pretty much, we kind of know what we could do there, and we've got programs in place. Crew's a different kettle of fish, in my opinion. I believe that we do need high thrust systems for crew transportation because of the trip time requirements. And cost, we've all seen the sumo wrestler chart this morning. Cost likely constrains these to chemical or small NTP systems, in my opinion. So what are the affordable options? We consider LOX methane with ISRU to be a pretty affordable option. A lot of LOX methane engines have been tested quite successfully. There are good architectures for ISRU on Mars for that propellant. LOX hydrogen, again, it's a hard cryo. We were talking just before the session started. You can do soft cryo or hard cryo, and there are trade studies. There are trades between those two from a performance and risk perspective. Nuclear thermal does, with long-term cryo, it's a hard cryo, so you got to store it for many, many months, does provide you with the least number of launches. It's the lowest total IM LEO option. So again, SEP crew, NTP, SEP cargo, NTP crew is the lowest overall mass, as you would expect just from the rocket equation, not a big deal. There is what was presented earlier today, and also a study out of Langley that is looking at, what if we can relax the crew transfer time. So the crew transit times during the JPL discussion this morning were 200 to 250 days. That's okay. There's a storable chemical option. And so that actually is much nearer term if those transit times are acceptable and we can get around all of the human health issues. And so again, big question in my mind about the crew transportation options. So chemical options are high TRL, but they will require more launches with potential for in-space assembly. There may be some ways to mitigate some of that. Again, hard cryo or ISRU. And then nuclear thermal is lower TRL, requires long-term cryo, and as Mike was just saying, there is a real cost risk associated with NTP. It's a big cost potential issue. So I talked a little bit about that. You know, Mike already talked about the benefits of it, but the safety and regulatory issues really drive the cost of NTP. I mean, that's the bottom line. And in order to successfully find an affordable way within that budget plus inflation line that was shown this morning to drive this, we've really got to take a hard look at the DDT&E program approach. We've heard what that was this morning, so you should all be very familiar with that. The fuel selection, Mike just talked about LEU versus HEU. Very big cost driver there. The thrust class, what thrust level do you want? Do you do multiple smaller engines that are easier to test, have a smaller footprint for your testing programs, and overall, you know, the per engine cost is lower some, but you need more of them. So that is a trade that needs to be done. Again, you can drive your DDT&E costs down by virtue of modifying these, by looking at this, but it's still going to be expensive. So we got to take a hard look at this. So I've already said, actually, we recently did a paper at the NETS conference in February looking at driving down the thrust requirements of the Mars, of the NTP using SEP cargo. So just a 100 kilowatt cargo vehicle enabled you to really decrease the thrust level required for the NTR, the nuclear thermal rocket. So no big engines with big footprints, and again, the key is use as much off-the-shelf technology as possible to drive your overall DDT&E cost down. I'm on my summary chart, so I think I'm buying you back at least a minute. So the cool thing is, I was at the National Space Symposium, and Charlie Bolden gave a speech there, and he said, you know, I think he may have said this yesterday morning, but we've never been this close to Mars. And the really cool thing is that for the cargo and the pre-placement, the logistics planning, we actually have programs in place today to do that part of the mission. That's really a pretty big statement, actually. We've made a huge amount of progress. That's not just on the propulsion side, it's also the power side, right? So you got power, propulsion, and you got to integrate that into a module. And those efforts are underway today, so that's very exciting. We now need to take a harder look, somehow or another my summary chart vanished, at the crew side. And that's a different kettle of fish because there are lots of different requirements for getting the transfer times down. So I'll end there. Thank you.
Thank you.
Oh, sorry, thanks. I know I was going to forget something up there.
Okay, my name is Mark Carter. I work for Astra Rocket Company, and I'd like to say thanks for inviting me to this conference. I've enjoyed it much more than I expected. I have never been to this conference before, and I'm impressed. So thanks for inviting me. I'm going to be talking about sustainable human exploration with electric propulsion. And next slide, please. Oh, I got to do that myself, don't I? Okay. So I think we've been seeing this a lot in this meeting, which I didn't realize that the paradigm had really switched as much as it has, but already you've seen the two sort of thought processes coming in over the last 5 years have been Apollo-like, which are not really sustainable architectures. You take everything with you, and there's no, it's one-time use, and it requires big throws, and I think everybody now agrees that this flexible approach is much better, and it becomes sustainable when you add electric propulsion to that mix. So these new technologies are coming on board, Vasimir being one of them, which I'll talk about that a little bit more in a minute. But the main purpose, my boss is an astronaut. He's very concerned about the risks for human explorers. He's been in space 7 times, and he knows what can happen. Solar powered tugs and cislunar operations are a great place to start. You can test your new technologies, you can test your ops. You can do a lot of support work so that you can leave from lunar orbit. And so this is a first sort of step that you have to take to get expanded out and remain sustainable. You can't just start from Earth every time with everything that you need to take. You have this departure staging. Everybody's talking about this now, so I don't really even need to talk about this anymore. We need to build infrastructure. You need something for ops at Mars. You need to pre-position whatever you want, and then you need to follow up with fast delivery of explorers or anything that's perishable, anything that you might need, or emergencies. So I'm going to do a little bit of a segue into the propulsion basics here. I was thinking that the people that are actually going to be going to Mars are probably in grade school right now, and so I'd like to explain some of why we want electric propulsion to them too. But first I'm going to talk about variable specific impulse magnetoplasma rocket, that's VASIMIR, and it is a steady state electric propulsion system, and I'd like to say thank you to NASA. We just recently received an award to integrate our thermal management system in with our rocket design, which we've been doing physics testing on since 2010, or really 2009. We've done all of our work with private funding up until this point, and it's really nice to have a little push from the government. The VASIMIR engine does provide continuous thrust, and so with these types of missions, you accelerate continuously. There's nothing to really slow you down. It's low thrust, but you have a long way to go, as we've been pointing out, 100 or 200 times further than you had to go when you go to the moon. So you have a long time to accelerate. If you save your propellant and use it over the course of roughly half the distance there, you turn around and then slow back down so that you can capture as you get closer, you can dramatically shorten your travel times. Alternatively, if you don't want to go so fast, you can also take a much bigger load of cargo ahead of time to pre-position assets. VASIMIR receives power from any electrical source. It can be a solar array or nuclear electric power, and I'll talk a little bit about the transition from the solar to nuclear power sort of threshold, what you can do with what we sort of have now, what you might need to do if you really wanted to take things so that you could go routinely to Mars. VASIMIR converts hot gas into a plasma jet. We do it differently than you do in the other types of electric propulsion systems, or most of the other ones. So we use radio frequency waves to both generate the plasma with a helicon source, and we use ion cyclotron waves to accelerate the plasma and expel it out the end of the nozzle. So these systems are much different in their PPUs and in how they interact with the plasma. The plasma never has to be separated into ions and electrons separately. The natural modes of the plasma, which have been studied really for 50 years in the fusion community, are the best way to exploit the plasma without having to separate it. It avoids what we call charge separation. It helps limit the voltages. You're trying to drive a natural mode instead of basically something the plasma doesn't want to do, so it's much more stable. And that's a major difference, and it makes our power processing units are much simpler than you have with other types of propulsion systems like Hall thrusters or ion engines. It also has a very strong magnetic fields in it. We run about 2 Tesla, a little under 2 Tesla in our system for experiments. And that protects and provides effectively a magnetic bottle that prevents this hot plasma. We're talking about millions of degrees type plasmas. It prevents it from interacting with the surfaces once we go into the acceleration section. That's a big player in terms of longevity. If you're doing tugs or round trips, you really don't want to relaunch your asset here. You want to use this propulsion system as many times as you can. You want to go to Mars, come back, or maybe you do different types of, go from Earth orbit up to lunar orbit, various things like that. But you really want something that's going to last for a long, long time, that you can just bring up more prop with you, add it onto your system, and just keep on going. We offer also many propellant choices for in situ or for other things too. You can do hydrogen, helium, neon, argon, krypton. We can also do xenon. Xenon is actually more difficult for us because it requires higher magnetic fields. It's a little bit opposite from other types of electric propulsion in that regard too. We can also do iodine and things like that. We have not tested those because they are expensive and difficult to test, but anything that basically produces a gas feed into our system we can handle. And so I'm going to go back a little bit. Why is it that we need this electric propulsion? And this is some rocket basics. If you go to your chemical thrusters, you're combining your power source for your propulsion with your propellant. So you have an oxidizer and fuel, you burn it, and you expel it out the back. And this is the classic thing. that everybody has typically done. With electric propulsion, and it doesn't really matter which type of electric propulsion you use, you have your propellant separated from your power supply. So this power supply could be a solar array in this example. And it provides the energy that you need to ionize this propellant and heat it up to millions of degrees. Here you have thousands of degrees. Here you have millions of degrees. You can use a lot less propellant if you go to the high velocity, high ISP systems, because momentum is mass times velocity. More velocity, less mass. And here's another reason why you really want to go to the electric propulsion is that chemical rockets are really great for getting off the ground. There's no substitute for those, quite frankly, although maybe some NTR might be able to do it, but I think most people would rather stick with chemical, at least the LEO. But they do have serious limitations as soon as you go beyond low Earth orbit. And that's because when a rocket is going faster than the exhaust plume coming out the back, you get this strange effect. If you imagine you're standing here looking at the rocket go by, I apologize for my little cartoon here, but if the propulsion, if the propellant is coming out the back slower than this rocket is going, this exhaust plume is going to continue to follow the rocket. It's going slower than a rocket, but it's still going the same direction. So in this one-dimensional picture, the rocket goes out here and stops. Eventually, that cloud of gas propellant is going to catch up to it. Well, that's obviously pretty inefficient. The best chemical rockets expel their propellant at about 4,000 meters per second, 4 kilometers per second. And if you look at low Earth orbital velocity, that's 8,000 meters per second already. So already you can see chemical is starting to have some troubles in terms of you have to have a lot more propellant because you just can't use it as efficiently as you'd like to. So the other thing we want to do is go faster, especially to go to Mars. And so to go faster, you need this hot exhaust. So if your propellant is going faster than the rocket needs to go, anybody, observer sitting here watching the system go by will always see the exhaust continuing in this direction and the rocket going in that direction. And that extra efficiency requires very hot exhaust. And at this state, you're into plasmas. So that's where electric propulsion comes from. So here's some estimates that we did. It's actually been 2 or 3 years ago that we last really looked at trying to go to Mars and what types of requirements you have to have for achieving different goals. Some of this is a little bit outdated, but mostly it's still relevant. So I'm going to talk about staging departure using solar electric power tugs to get things ready near the moon. I'm going to talk about prepositioning infrastructures a little bit, and talk about round-trip missions for humans that could be done in less than 1 year. That allows you to have abort options and all sorts of things. What do you need in order to do that? And let's see, for some reason, there it goes. So for sustained exploration, we really want cost-effective logistics. You want to minimize the number of launches. You want to maximize how much material you get there. You don't want to take anything that you don't absolutely have to have, and you want to put everything you can ahead of you. And so heavy launch to LEO is good for that. Solar tugs to L1 or wherever you want to go near lunar are also good for that. Our present Vasimir design, we call it a thruster core 1. That's a single thruster core that handles about 250 kilowatts of electrical power, processes that much electrical power, and has efficiency of about 70%. So about 70% of the power that you put into the system is going to be directed in the direction that you want to go, jet power. So you can have a system here that runs 50 kilowatts to a megawatt or more. The plasma physics, these waves are not density limited. They can scale up to larger systems. But you can see our mass here is only 2.6 tons for the whole system. That includes the cooling systems and designs and everything for a 1 megawatt system. That's very low. That's actually less than the solar power supplies are going to be doing. So you have a nice, very low mass propulsion system. Let's see, so I'll skip through this pretty fast. This is what you can do if you want to move a big assembly, assemble it at low Earth orbit, and then move it with a solar tug out to somewhere in the vicinity of the moon. We chose L1. You preposition it, Mars, your various other things, and then when you're ready to go, you do an SLS launch and load the crew up. So you basically do boarding just like you do an airplane a little bit. You bring the crew on last, or the passengers on last. So we've been basically using the DRA-5 payload as our baseline, which apparently now they're being able to cut down the mass a little bit, which helps. But one thing that you get into when you try to do this, I was going to talk a little bit about the nuclear threshold of what you actually gain. If you use chemical to try to move this type of a payload all the way to Mars, this is how much rocket fuel you have to use compared to the size of your rocket engine and your payload. If you go to nuclear thermal, you get a gain in a factor of 2 in your ISP, but you still have quite a lot of propellant that it takes to achieve this mission. If you go to nuclear electric, and we're using 3,000 seconds to 10,000 seconds variable, which we can do that with our system, and 10 kilograms per kilowatt, which is achievable certainly with solar based on present designs, but could possibly be done with Brayton cycles on nuclear electric as well at 10 kilograms per kilowatt and about a 15 megawatt system. And this is the stack up that you have at L1. So you can see where nuclear electric really starts to help is if you can get your system so that you can get there and back in less than a year. That means you can abort. You can do all kinds of things that you really can't do otherwise. You're having to wait for the orbits to come back in a line. So you can come back and catch up with the Earth before it gets completely away from you if you can get into this range, and this is where we chose 10 kilograms per kilowatt. Solar power right now combined with Vasimir can actually get very close to this curve. And so if you drop your payload from the 65 tons that we were talking about with DRA-5 down to 6 tons, it's sort of roughly the same sorts of things. You can still do fast transits, but I don't think we're going to get humans in a 6-ton payload. It just doesn't seem very likely. If you carry this all the way to the extreme limit, we've been hammered for this 39 days to Mars thing, but this is just really an asymptotic limit. If you look at NASA projections for the lightest you could ever get nuclear power, and they are pretty far out there, and Vasimir does continue to scale better with higher powers. It might be possible to do this, but it's not really necessary. Quite frankly, when you get into regions that were already achievable in the fairly near term, you can already achieve this transition to 1-year type round trips. And so you also have much wider launch windows, which is a big advantage of electric propulsion. And chemical gives you no abort, and NEP allows all kinds of options. And again, thank you.
Mark, take your. You want to pass that down too? Yeah. Okay, that concludes the panel presentations, but we do have plenty of time for questions. And I have some questions up here, but I'd really like to start out and see if there are questions from the audience, and I'll use mine to fill in if we don't. But if anybody has any questions, please come to the microphones, and we'll go from there. So, yes, sir, go ahead.
Thank you. Mike, nuclear thermal options, are you really looking into leveraging all the modern reactors that look at solutions for green technology on the power grid to see what you can glean and learn from all of that work? I find it hard to believe that you have to do everything again from scratch with all these new modern designs of efficient reactors that are out there. And if you go to lighter or different elements, what's the upper limit for temperature and ISP you really think you can get? Because I think you can beat Vasimir hands down.
Trying to start somewhere, yeah.
The gauntlet has been laid.
That's right, yeah. So the definitely going to benefit a lot from the tremendous advances in nuclear technology. I should mention, many of you may have heard China recently announced that they're going to put 4 pebble bed reactors. I think they're going to start construction in 2017. They'll have them on their grid by 2021. They have triso particles. So those triso particles were actually developed based on the fuels we were developing in the rover NERVA program. The bead-loaded graphite version eventually led to the triso particles. So there's a lot of interplay. So we will learn a lot from the advances in our fuels codes, in the general design approaches to nuclear systems. The issue comes in is we're the only people that want fuel that'll run to 2,800 Kelvin, maybe 3,000 Kelvin. We used to try to say, well, maybe our normal operating conditions for the fuel would be analogous to your worst case accident conditions, and they say no, our worst case accidents never get that bad. So it's that's kind of why we're being driven to these exotic materials. So not a lot of people work with tungsten-based cermets. Not a lot of people working with the carbides, the graphite composites. But so in specific areas, the NTR is very unique. And we'll have those unique requirements, but in other areas we will benefit tremendously from the advances in nuclear power.
Like just a brief defense of Vasimir.
Yeah, hey, I didn't do anything.
I'm glad there's someone between the two of you there.
Yeah.
2,000 Kelvin, 3,000 Kelvin is very hot, and that's very good. You're going to get the specific impulses of around 1,000 seconds, or maybe a little bit better than that. But if you really want to go to 10,000 seconds, or if you need higher ISPs, you really have to go electrical, because some kind of EP, it doesn't have to be Vasimir per se, but you need higher ISPs.
Now, one of the things to build on that, and Mark mentioned a lot in his talk, was with these fuels, because they are designed to run at very high temperatures. Their fuels that were demonstrated in the 60s that could run 2,000 Kelvin for over a year at high power densities, and that was, we could build on those. If I had that type of a hot side temperature available to my power conversion system, that's what allows a very low mass, high performance reactor that could then be used to power an EP. Of course, even if I get the reactor that can run that hot, I'd still need the power conversion. But it is on the path. So there's, we were talking about commonalities, and there are a lot of commonalities that we could potentially take advantage of.
Question over here.
Yes, I just had sort of a general comment, but I don't know if it's just my perception, but I'm encouraged by the fact that it seems that the taboo, to an extent, has been lifted on the discussion around nuclear propulsion. It seemed like just 2 years ago, everything was discussed and nuclear was sort of mumbled out of the side of the mouth, maybe at the end of the presentation. But now it seems it's obviously part of the discussion, at least now back in the public realm. So I was wondering, has there been some sort of phase shift that has made that more of an open discussion? So that's one thing. Now, I also had just one specific for Mark. I know Dr. Chung Diaz, going back as early as the late 70s, was coupling his Vasimir system with fusion energy, fusion power. I was just wondering if that's still in the discussion. Are you still in discussion with that community, or has that been shelved?
I worked in the fusion community for 23 years at Oak Ridge, so that's where I learned how to use RF plasmas. Fusion requires confining a plasma instead of letting it go. So the best thing you can do when you have a plasma is let it go. It will go unstable. And if you follow the fusion community, you'll know that it's very difficult. Very large reactors are required for fusion. It's ultimately a low power density system. I love fusion. It's going to be cost competitive. It's probably not going to be cost competitive on the Earth for quite a while.
Right.
And in space, it's way too heavy. The fission reactors, like Mike's talking about, these Cermet reactors, if you hook those up with a Brayton cycle, one nuclear electric, look like a beautiful, fairly easy, well, easy, it won't be that easy, but a straightforward thing to approach, a way to approach electric propulsion. You really want the ISP. And the further you go, the more you want the ISP.
Right.
Just to address your other comment, I wouldn't say that there's been a phase shift. I would say that there's been a increased recognition that Mars is feasible. And what that's meant is that we have to take a really hard look at the crew transportation, the crew transit time. And they're looking at all options for that. And the key is it's got to fit within the annual budget, as we heard about a lot,
Right.
this morning. And so that's part of the reason why the work that Mike is doing on, affordable NTP is really important to answer that question. I don't know what the answer is, and if you'd seen the last bullet of my summary chart, this isn't about one technology or another technology. It's about what is the most affordable way to get humans on Mars, right? Whatever the answer is, doesn't matter what the answer is. Let's go do that.
Right.
And so, I would say people are taking a really hard look at that, are starting to take a really hard look at the crew part of the transportation. That's why this is coming to the fore.
All right, thanks.
All right. Yes, sir.
Well, just on that last exchange, I must say that I worked for 5.5 years for R.W. Bussard, who designed Kiwi A, the first rover. And much as he loved it, he wanted to go to fusion propulsion.
Of course.
And that's what he was working on when I worked for him. I carry around in my pocket a presentation that has a slide in it that compares various propulsion technologies, and a few of the numbers in there are kind of pertinent to what we were looking at. We're talking about what sounds impressive, 50 to 100 kilowatt systems. And the slide starts with the Instar Deep Space One propulsion system, which I think is about 3.2 kilowatts, and it shows an Essex arc jet at about 23 kilowatts, and then it shows a Piper Cub putting out 180 horsepower, which I believe exceeds your 100 kilowatts. So that's I think, important to understand how low a power 100 kilowatts is, and why we really can't take people with something like that. It's way underpowered. Slide also includes Vasimir, but it ends with the space shuttle main engines. And I back calculated the rate of oxygen consumption on those to get the power, and each of those main engines is about, I think, 6 gigawatts.
Right.
For a very short period of time.
8 minutes. But I mean, that's but it's also a hydrogen-rich exhaust, relatively low specific impulse, but it does give an idea in the gap in power we're talking about from what we're used to as a rocket and the sort of things we use to get into low Earth orbit and the sort of things we're talking about for space propulsion, that we really need to work on the power sources for these things.
Well, I'd like to follow a little bit on it. It's really a gap in energy. If you integrate
Right.
the total amount of power, if you can push your system for, 2 months at much lower power levels, it's that integral. That 2 months is a lot longer than your 8 minutes. And so your total integrated power is what ultimately gives you your delta V that you need,
The amount of energy.
the amount of energy
in the-
that you need to get to your next orbit. So you need to think about it in that way a little bit. Now, the power is an issue. There's no doubt about it, and I agree completely. 100 kilowatts for humans to go to Mars
Forget it.
is not going to be possible. I mean, unless you can get them packed into, naked, taking a guy naked there.
No, but that's why nobody's talking about that.
Well, and-
Nobody's
and when-
suggesting doing
and when,
that.
And when you people are talking quite rightly that this is a neglected part, getting from planet to planet seems to be the neglected part in this, and everybody's looking at landers and rovers and habitats and stuff like that. This is the underlying driver, and it's huge. It's absolutely huge in the overall economics of what we're able to accomplish in a target like Mars. And it's seriously underappreciated. Got to get some juice up there.
You're
We
hired.
agree.
Okay.
To put it mildly.
Probably the last question. We have to break for the next
I was
panel.
at this conference last year, and I asked about Vasimir, and they said it was a fine idea, but you need a reactor to power it, and therefore it was basically not going to happen. I take it something has changed in the meantime. What hasn't changed is the outside hostility to nuclear power. The usual, you put a reactor, talk about putting a reactor in space like this, the usual suspects are going to scream bloody murder. How are you going to deal with that?
Well, I'll go ahead and take that one. Vasimir does not require nuclear power. That's something, a misinformation I'd like to get rid of. It doesn't care where the electrical power comes from. It can come from solar, nuclear could be fusion, fission, don't really care. So that point is really an issue. Solar power can probably scale up. How many of these arrays can you build up? Maybe you can get to a megawatt. Never bet against your kids. Your kids will figure out things you never. So those kinds of things are possible. Going to a megawatt with solar allows you to do a whole lot with cargo. It allows you to do, even at 200 kilowatts, you can do a lot with cargo. But the main place where Vasimir is most interesting to us is commercial aspects. There's not really, defining your customer when you're going to Mars becomes a NASA mission or an international mission, however it's going to be. The commercial applications will definitely be solar near Earth.
And I guess I would just say it's to me it's a tribute to Department of Energy and NASA as far as the public information activities. If you look at the history of nuclear launches, the New Horizons, of course, which is going by Pluto in July, there was actually fairly minimal opposition to that launch because it was clear that a nuclear power system was needed. Mars Science Lab, there was even less opposition because when the public looked at it, but they also had to have the right information. It wasn't again full credit to Department of Energy and NASA, the individuals that work in that area. It wasn't if someone asked a question, it wasn't a no comment or we'll go back. I mean, they addressed the issues head on, they engaged the public early, and by doing that, it was very clear from our science lab we needed the power for that rover, and so the benefits were very high, and the risks were well explained. And so with if I'm talking about a nuclear powered system, then I need to get the astronauts to Mars and back quickly and safely, explain the benefits, and then let people ask questions, explain the risk. Noted very briefly, fission does have the advantage that these systems are essentially non-radioactive at launch, and so it's a lot of pros to fission, but there will still be a lot of questions, and so we would just need to address that very early. But I think recent history is on our side because, again, the last two nuclear launches have gone very smoothly, and again, that's a tribute to the personnel at the Department of Energy and NASA that worked in that area.
Yeah, I think personally it's going to come down to money. We need to find affordable ways, because chemical is an option. It's got its pros and cons. We're going to have to address it.
Yeah.
From a
No, I
finance.
agree. Yeah, we have warp drive, but if you can't afford to build it, it doesn't matter.
Yeah, I'd like to comment again. You know, a debate between nuclear and electric propulsion is probably not helpful to the cause. I think ultimately we need high power, and I think we know what it's going to take to get that. But we have some momentum now for modest level electric propulsion development and demonstration. I hope that we can maintain that, because I think that is, in any path we take, the first steps that we need to take. So hopefully we can keep the momentum going on that as well.
Yeah, we need to finish the path that we have started down. Show that we can do that.
And on that note, we will conclude the panel. Thank you very much.
Thank you. Wow, done early. We have actually time for a 10-minute break. So see you back here at 3:30. Thank you.